Previous speaker focused on towed streamer marine, and as I used to say at RXT, the future's on the sea floor. But anyway, I'm going to talk about what we've been doing recently to try and improve the cost efficiency of ocean bottom seismic. It's been well recognized for a number of years that putting stationary sensors on the sea floor gives you better seismic data for a variety of reasons, and Ian's been well known for publicizing that. But one of the prohibitive aspects to that is that when you have stationary receivers, the cost goes up. So what can we do about it? So I'm going to talk a little bit about some work that we did in the Gulf of Mexico starting in 2012. So this is the outline of the talk, a little bit about the motivation, the actual enabling technology that allowed us to develop the use of the blended sources, so both from an acquisition and processing perspective. The actual survey design, how we blend and deblend sources, what the implications were for survey duration, and then some conclusions. So it's been well recognized that using wide azimuth or multi-azimuth data, especially of complex overburdens, salt, not other geologies, gives you really improved imaging. So you go for increasing azimuth, improves data quality if you can handle the imaging side of it. And example here, for courtesy of BP, just cut off at the bottom there, but showing dramatic improvement in going to a wide azimuth solution. So when Apache approached us in 2011, they wanted to get wide azimuth imaging off the Louisiana coast, but they had 36 producing fields in the survey area, and they wanted to try and get full azimuth, wide azimuth imaging, because some of the structures had salt overburdens, and the answer, of course, is to place the receivers on the sea floor. So that's fine. And as I say, people have known for some time that even without going to a wide azimuth solution, you get better bandwidth data from the sensors on the sea floor. But the problem is how to get the cost down. And it's pretty simple. It's not rocket science. You need to use a large receiver spread to try and remove what is essentially the essential flaw of ocean bottom seismic, stationary receiver seismic, with small spreads, is the number of duplicate shots. Some of the surveys that have been shot in the North Sea have had the shot points have been fired 8 times in order to get the coverage. So you want to improve the size of the spread you use. You need to improve the efficiency of the ocean bottom sensors. Typical OBC performance compared with towed streamer has been quite limited from an operational perspective, primarily because you are stressing and de-stressing the cables, connectors, terminations, etc. every time you put them on the seafloor and recover them from the seafloor. And as somebody pointed out to me, if you were doing the same thing, if you had to pull the streamers in every line change for towed streamer, you'd end up with the same kind of technical downtime that ocean bottom cables have suffered from. And then on the source side, you need to look at how you can reduce the source effort and then reduce the source time. So the enabling technology on the receiver side to use a large receiver spread and improve receiver performance. I work for Fairfield Nodal, so I would say that, to quote Andy Rice Davis. The node technology that we introduced into the industry in 2009 has proven itself to be extremely reliable and successful. In over 300,000 node deployments, we've had more than 98.7% data recovery, which makes it probably the most reliable seismic system that's been deployed. But the important thing is that we can essentially deploy an infinite number of nodes. Each node is a self-contained 4-channel recording system, and they don't even know about the existence of each other. So you can have as many nodes as you like that makes economic sense for the project, and you can deploy those in any configuration. And because you've eliminated the traditional sources of ocean bottom cable technical downtime, there are no connectors, there are no terminations, there's no power distribution, there's no data telemetry, you actually get much better operational performance. So you can put a spread out, and we ended up with a spread with 5,200 nodes live on the sea floor, which we think has been the largest that's been used so far. We can deploy that and start shooting directly because we don't have to troubleshoot the spread. On the source side, we want to reduce the shot effort, and we want to reduce the shot time. And so the survey design that Apache decided upon and we enacted was actually a single-sided acquisition, and I'll explain what that is in a second. And that reduces the shot effort by about 40%. And I'll talk a bit about that. And then going to blended sources or simultaneous sources, so we're firing two sources essentially at the same time, or quite the same time, as I'll explain. And that reduces the shot time by about almost 50%. And the concatenation of the single-sided acquisition and the blended source acquisition, actually reduced the survey, which we originally estimated was going to take 30 months. We shot it in 11 months. So it's quite significant. So the actual survey design, as I say, there are 36 producing facilities in the survey area, in the main pass area of the Gulf of Mexico. Many, many different geological objectives, some in the current target, some in the deeper target, where people are looking for deeper gas. Apache wanted wide azimuth data, ideally full azimuth, but there's a price to pay, to image around the salt piercement structures in some of the survey areas. They did have previous narrow azimuth OBC data with an east-west orientation, as it happened. And the ray trace modeling and examination of some of the streamer data from previous acquisition, they determined they needed 9-kilometer offsets in order to image the deep targets they wanted. And so taking that in mind, we ended up with this kind of survey geometry. Vermeer hates it because it's not symmetric, but it's cost-driven. And so the bluey-green is the northwest or north-south oriented receiver lines, even though the dots look like they're lining up east-west. So the receiver lines are laid north-south. The shot area is shown in red. The shots actually overlap the receiver area as well. But it's single-sided in the sense that we're only shooting to the east of the survey area. An orthogonal geometry was selected to get a wide azimuth solution. 250-meter receiver line spacing, 250-meter shot line spacing, with a 50-meter source interval. And on the 50-meter receiver interval. On the source side, this is where we started to take into account some of the work that's been done at Delft University in the Delphi project on blended sources. And we decided to use a pseudo-random shot point location. So each vessel, and we have two vessels, one of which starts off at the southern part here, the other one starts off here shooting this way. And they run autonomously. They're completely independent, firing the shots on pseudo-random pre-plots. So if we needed to go back in and do any reshoots, we would use the same pseudo-random pre-plot. If we want to do a 4D, and there are some issues about 4D we can discuss, we'd use the same pseudo-random shot point location. So the cartoon here, this is just taken, and I'll show you some more information. So we have, on average, a 37.5-meter shot point. The reason this works very easily with the nodes is that we have continuous recording in the nodes, so we can have any shot point interval. We're not trying to synchronize to a fire time, any recording, and we can have any record length we like. We can actually decide the record length after we've acquired the data. The spread that was used was a 12 by 17.5 kilometer spread, 4,200 nodes, and then during the course of the 11-month survey, we actually ramped that up to a 15-line spread. And I say we believe that's been the largest ocean bottom spread used so far. So I say single-sided acquisition. People say, well, why'd you do that? You know, because I said, well, it's driven by cost. And this cartoon here, I just took and cut and pasted this. If you shot this with a narrow aperture towed streamer, you'd end up with single-sided acquisition, but you'd racetrack it. So you'd have single-sided acquisition to the east for the first 3 or 4 kilometers of the survey, and then to the west, and then to the east, and then to the west. And the reason why people don't make it bi-sided is purely cost. Shell call it anti-parallel. It's been done a few times in the industry, but in general, people don't do it because it's too expensive. And so, in general, people, when they put stationary receivers on the seafloor, shoot bi-sided because it's relatively easy to do so. But it puts the cost up. And when you're looking at a 2,200 square kilometer survey area, as I say, going to this single Vermeer non-approved acquisition geometry it reduces the shot effort by 40%. And so that's the reason why it was selected. So just to put it in context, this is the receiver area and the shot lines extending 9 kilometers to the north, 6 kilometers to the east, superimposed on the M25, or Greater London. So it's a pretty sizable spread. Just to look at the acquisition geometry, this is the illumination plot. I say it's a wide azimuth, it's not a full azimuth. To make it full azimuth would have added 40% to the shot time, so we actually looked at this. And then by combining this with the previous ocean bottom data, this is the resulting illumination pattern that Apache deemed was sufficient for their purposes and matched their budget. So in terms of blended sources, there's been a tremendous amount of work done, especially in the Middle East. BP, BHP, Aramco, PDO, Shell in Oman have shown using simultaneous sources, vibrosize primarily, tremendous improvement in data quality and a huge improvement in productivity. There's been very limited uptake so far. There's been some tests done in the Gulf of Mexico. There's some multi-client, multi-coil core shooting with simultaneous sources. Survey that Apache shot in northwest Australia, where they fired flip-plot sources with the dither together, and some OBC work that BP have done in Trinidad, but it's relatively limited. It's slightly surprising because, as you'll see, as I've mentioned, the actual bottom line is significantly impacted by being able to reduce the survey duration by going to blended sources. And from the work we've done so far, and hopefully the results will be coming out from Apache later this year, is that there's arguably no degradation in image quality. So initially, following the work that Apache had done in Australia, where they fired the two sources very close together in time and space, on the philosophy that you want to have large arrival energy coming in at the same time as large arrival energy, so you don't have the large energy from the interfering source arriving at the same time as small reflection energy from the desired source. We did some tests and have a look at it. And we used the deblending approach, as a blending deblending approach that's been proposed and documented by Delft University. In fact, we actually hired the guy from Delft University who did his PhD on this, despite the job offer from Shell. And so this is tests that we did where we have the sources close and synchronized. So we're firing the two sources close together. It was about half a kilometer apart in this case, where we have a plus or minus 500 millisecond dither controlled between the two sources, and this is the result. So this is the blend, unblended, and when we deblend it. So this is both sources together. This is when we've deblended it, and this is the difference. What we found was that when we actually went to an unsynchronized comparison, we actually got a lower deblending noise or deblending residual by about 10 dB. And it would appear that the offset between the sources has no impact, in this particular area at least, on the performance of the blending approach. So this is that same slide again, and then this is when we go to completely unsynchronized. So we have the completely random firing of the second source compared with the synchronized firing in the dither, and it's about a 10 dB lower residual. So this is what we adopted. And just to look at some tests we did, where we looked at these are synthetic, and the argument here is that we actually have more noise in the synthetic than we had in real life, because we're adding two sets of noise to the data. We can discuss that philosophical point later over the drinks, perhaps. So we're looking at the common receiver gather for the node. You'll see the blended noise appears randomly through the record from the interfering shot, and this is at different shot offsets into the same common receiver gather. And when we deblend the data, this is the result. And the deblending performance, if you look closely at these reflections, or so the deblending performance appears to be completely independent of shot separation for this particular approach, which has major implications for survey design going forward. So the actual deblending that we've adopted to actually try and sort out the firing of two sources into the same receiver, it's a highly underdetermined problem, and you want to try and optimize it, and you have to apply some a priori constraints to the optimization. And to do that, we need to know the exact time and the location, the approximate location of the interfering source, and so that we can control the timing relationships. From the continuous data set that's recorded in the node, we extract the sources, the data according to source A time and source B time. We try and suppress the information for source B. And we use the coherence of the desired energy against the incoherence of the undesired energy to actually filter out the two data sets. So if we have, this is slightly small, but basically we've got a receiver line sitting here, and we've got shots going, showing just 4 shots here going into here. So from the continuous data record in the node, and these are common shot gathers, we have extracted the data from the nodes corresponding to these 4 shots. If we have 2 sources firing now, so this is the source A firing, source B firing, in the common shot domain, this is the interfering noise that we see for the same records coming from the interfering shot. And so what we do is, and then from the same data record, so this is for the source A times, this is for the source B times. So the noise that appears in the source A records for source B is actually a coherent shot when you refer it to the source B times. So that's in the common shot domain. Well, the actual process, say, been developed by Delft University, and we've just basically followed the same approach, where they call the input data pseudo-deblended, and then we actually go through in the common receiver domain is where we apply the data, apply the filter, and we do an iterative threshold coherency estimate. So we look at the coherency and incoherency of the data, and we basically take away the lowest hanging fruit. So we take away the most incoherent energy and then iteratively repeat that until we end up with the results that you see. So in the common receiver domain, things look a little bit different. So we have for the continuous data record in the node, we have the common receiver gather for the node, and the interfering noise appears all the way through here. And this is for the source A times. For the source B times, it's the same data set, and so the noise here is now coherent because we use the right fire time, and the coherent energy from source A now appears as random noise throughout the entire record. And the reason it appears throughout the entire record is because we've used a pseudo-random shot point location for both sources. So this is what it looks like in the common receiver domain blown up. So source A time, interfering noise, and after the deblending process, this is what we end up with. And this is just taken from the navigation files from these are the receiver lines, these are the shot positions, and you'll see there was some downtime. We don't perform miracles, shot sources do go down, but when you blow it up, you'll see we do indeed have a non-uniform shot spacing, and we actually force, and we use a pseudo-random distribution for this, we force the delta X between the shots to range essentially uniformly between 25 and 50 meters. So we have an average 37.5 meter shot point location. And this is what makes the technique work. So this is the common receiver record for source B time, and when we apply the deblending process, this is what we end up with. So looking at it in some detail, this is taken from a fire line, so the move out's quite low, and you see the interfering noise coming in bursts of some detail. And when we first apply the deblending process, we ended up getting this result, and we actually had some additional shots in here. And of course, we actually have mitigation shots when we're taking a line change. And normal practices, you don't log the position of those because you don't really care. All they're being used to do is to stop you having to go through a soft start because you're restarting again in terms of marine mammal mitigation measures. So the procedure on board for the first couple of lines was not to log the position of the shots in the turn, but we need to know that because we're recording continuously, and the vessels are operating, the two source vessels are operating continuously. So we actually need to know that. We also found out that Apache had got a high-res vessel shooting, doing a site survey somewhere off, and they hadn't bothered to tell us. But when we put in the information concerning, obviously we started logging the shots of the mitigation shots in the line change, because it's important for the other source to deblend, or the other records to deblend properly. And we put those in. We were able to remove those quite satisfactorily. But what's important to recognize is that without the a priori information, this other noise leaked through the deblending process, because it was not recognized, even though it looks incoherent, because it wasn't part of the incoherent energy we were expecting. The filter doesn't remove it. And one of the points we are very keen to make from a philosophical perspective is that we want to do no harm to the data in the deblending process. We would rather allow there to be some residual deblending noise leak through the deblending process so that some of the subsequent multi-channel noise processing, noise suppression processes will take care of it, rather than remove energy or change the amplitude of the recorded data. So this is the difference before and after. So this is the difference between deblend and denoise, just taking out the additional information. So in the shot domain, this appears as a fairly miraculous process. So going back here, we have very, very high energy interference with exactly the same move out as some of the desired energy. And when we apply the deblending process, lo and behold, it's gone. And so the reason this works, I say, is because we don't do it in the shot domain, we do it in the common receiver domain. And again, this is taken from the same data set. So this is the interfering energy. If I go back one, this energy here is now coherent. It's a long offset, but it's now coherent. And then this is the interfering energy we want to get rid of. And lo and behold, we do. So just to summarize, say taking some of the worst data examples, or the most difficult, if you like, data examples in the common shot domain. This is before deblend, this is after deblend. And we see it as a very robust and rigorous process, one that we will implement on board the vessels going forward. We haven't done it yet, but we will do it. So all the data you've seen so far has been hydrophone data, but the same applies exactly to the inline, crossline, and vertical geophone data. So this is the blended multi-component data taken, and if you look closely, you can in fact see the interfering noise, especially on the vertical sensor, less so on the horizontal and on the inline and crossline. And then the deblending, I'll toggle back and forward. Blended, deblended, blended, deblended. Works exactly the same way. Now for this survey, it was a PP survey. We're only looking really at dual sensor summation, so we're really only interested in the hydrophone and the vertical sensor. So in terms of survey duration, I mentioned this before, but the single-sided shooting geometry reduces the survey effort, the shot effort, by 40%. The blended source, because you have two source vessels rather than one, there's okay, they're autonomous, but there is a little bit of an increase in technical downtime. So rather than halve it, we reckon it was saved 47.5% rather than 50%. But by combining the two, going to a single-sided acquisition and blended sources, we reduced the survey duration from 30 to 11 months. And one obvious question is, well, if it's so great using two sources, why not use more? So I'm trying to encapsulate that in a slide here, and it's a little tricky, but bear with me. So if we take the configuration of a shooter and a node handler, so two-vessel operation, to deploy the nodes takes roughly 5 days. To shoot it takes about 10 days. If you have a nominal cost in whatever units you care to use, I'm saying it's kind of like the shooter's about 25 and the node handler's about 100. We end up with a cost per patch of about 1875. If we simply double the kit, we reduce the duration, but the cost per patch doesn't really change. What we did for this particular survey is we put a shooter, a node handler, and a combination vessel, a shooter stroke node handler, a hybrid vessel. It had source and node handling capability. So it's kind of like 2 for 1. So we end up with a 3-vessel configuration where we get the node deployment time, because we've got 2 node handlers. We halve it. We also halve the shot time because we've got 2 source vessels. One's a combi vessel. And the cost goes up, but we reduce the cost. Now, if we went to 2 shooters instead of 1 shooter, there is a slight reduction in cost. But this all assumes that everything works perfectly. And if we go to 3 shooters, the cost actually starts to go back up again. And when you plug in slightly more realistic downtime, because this previous slide assumed there was no change in the operational performance in going to a 3 operational vessels rather than 4, which, so putting it slightly more realistic, you actually see the costs starting to get almost the same. And we decided that for this survey, it really, the price break was so small that it just wasn't worth it. So for this particular survey geometry, the most efficient way of doing it was the way to use a shooting vessel, a node handler, and a combination vessel. Other surveys, geometries, other size surveys, you might have a different perspective. So, in conclusion, node technology, because of its inherent reliability, allows very large receiver spreads to be used. And that reduces duplicate shot effort. By going to a single-sided blended source solution, we reduce the survey duration by almost 2/3. The deblending approach that we've adopted, the Delphi deblending approach, has shown itself to be very robust in a production environment and operationally extremely effective. And by combining these latest developments in acquisition and processing technology, we've got unprecedented ocean bottom seismic performance. I would say that the separation independence of the deblending operator and deblending approach actually has significant implications for ocean bottom survey design, because we believe we can actually put 3 or 4 sources together very closely and actually put together a spread that we can roll as fast as we can shoot, which has significant impact for full azimuth exploration objectives. So with that, I'd just like to acknowledge Apache Corporation and Fairfield Management, and to thank the guys who actually made it all work, and to thank you for your time. Thanks a lot.
Thanks very much, Chris. Very interesting discussion on nodes that of course, a lot of people would just love to be shooting nodes all the time, but can't afford to do so. So it's nice to know that these developments are underway. I have a question, first of all. Of course, it's hugely expensive putting them down and picking them up again, really. Do you think the autonomous node that puts itself down and picks itself up has got a future? It's got a bit of a bumpy ride to start with, but do you think it's going anywhere?
You need to ask Panos.
Yes.
All things are possible. I didn't think I'd see anisotropic pre-stack depth migration run routinely in my lifetime, but I was wrong there too. Yeah, there are some fundamental challenges. I mean, battery power, obviously. I don't know much about AUVs, autonomous underwater vehicles, but from a basic principle, the last thing you want an AUV to be doing is trying to, you want it to be neutrally buoyant, so it spends most of its energy getting from A to B. And the last thing you want in a seismic sensor is to have no mass. So there are some fundamental dichotomies to be addressed there. But I'm sure they're solvable. I mean, the economics look very attractive. I mean, if you can actually get it to work. The node on a rope that we use, and there's 2 other node companies around now, or will be soon, that's actually pretty efficient. I mean, we deploy and recover at 100 nodes per hour, kind of independent of water depth. So for that 5,000 node spread, 5,000 node spread with 2 node handlers, we can pick up the patch in a day and deploy the patch in a day. That's pretty efficient.
time for a couple of questions. Yeah, one back, John.
Sorry, I may have missed it early on. What sort of water depth was that operation
I
in?
didn't mention, sorry, it's 70 to 400 metres.
Okay, that area,
Yeah,
70 to 400.
metres.
Okay, and you say your deployment is pretty much independent of water depth over that?
Yeah, yeah. I mean, we have taken the nodes down to 1,200 metres in the Red Sea, and the touchdown point's about 2.5 kilometres behind the boat. So we tend to slow down a bit there, just to position it. But down to probably 1,000 metres. And really it depends on the nature of the variability of the currents all the way through the water column as to whether or not you can achieve that. But if they're really predictable or stable, then yeah, it's kind of independent of water depth.
And then the other thing is in that particular environment, was there very much difference in bottom conditions for coupling purposes? Did the nodes all perform similarly to each other?
Yeah, there's several river flows coming into that main pass area, and so yeah, there's quite a lot of silt in some areas. It's pretty goopy, as they say. It's not all those quaternary sediments. We haven't seen any significant variation. I mean, you'll get an occasional node that's sitting on top of some local gas
stone.
Bucket. Not the stone will have sunk through the goop.
Oh, right.
It's to do with gas. I mean, it's very, very unconsolidated sediments in that particular area. So you end up, you can get some trapped gas. I mean, in some areas here, the P wave velocity is less than water velocity. And so, it's kind of unusual. But you will lose the odd receiver location purely because of the local bottom conditions. But in general, no, we didn't see any variation.
And presumably Apache are looking at process results now?
Western GECO are doing the full processing, so
Yeah, okay.
Time for another question or two? Yeah.
We'll have to be the other side of the room.
Next slide, Adam.
Andrew Wright again. Can you just talk a little bit about the? It seems that it took 11 months to do the survey. You've put the node down on the sea floor, so battery life recording must be an issue. But also, it's an incredible step of faith, if I understand it rightly, that Apache wouldn't really see any data for 11 months. They wouldn't know whether the survey had been successful or all those boxes were empty.
they trusted us. Quite clearly, the node reliability is an issue. Apache had used the nodes for some surveys they did in the North Sea the previous year. We actually do a full manufacturing test. We manufacture the nodes ourselves. We do that immediately before the node's deployed. The node cannot be deployed if it doesn't pass that test. So we have, I say, the 98.7% data recovery is a testament to the manufacturing quality assurance that we have. Once we get each patch, as you saw in my kind of cartoon slide, took 10 days to shoot. With a, and so that's deploy and shoot on average. So basically we have access to the data after 10 days. We go through, we produce brute stacks on board. We go through the normal onboard processing for ocean bottom data, and we actually do dual sensor summations on board and provide all that kind of information. So Apache, the QC guys that Apache employed were looking at the data like 2 weeks after the acquisition. There is a paradigm shift with nodal recording that says, and some people will not accept, that having no real-time contact with the data. The performance, what we found is that people have used the nodal systems, and we have a microstreamer we tow behind the gun arrays to give real-time seismic noise monitoring. We put down QC nodes. After 2 or 3 weeks, they go, okay, enough already, or stop, because we see the data's coming through. And so, but there are people who want to have it in real time, and we can discuss the reasons why. It's all to do with not ballasting streamers properly originally back in the 70s. Anyway.
Well, I think watch this space, because there's a lot of activity going on in the node industry.
Yeah, just one point. I mean, it was a very interesting talk from HSBC first thing.
Excellent was the word.
Absolutely, yeah, really. But it didn't focus enough on the ocean bottom side, where there is more demand than there is supply at the